Okay, this is section 8.2, exercise number 14, in which we're asked to use the direct comparison test to determine the convergence or divergence of the given series. And so our series here is the sum from n equal 1 to infinity of 1 over 4 to the n plus n squared minus n. So to use a direct comparison, we have to have some intuition about what we should be comparing this particular integral to. We know from experience that exponential terms tend to dominate polynomial terms. So this sort of 4 to the n is going to sort of have more of an effect on the behavior than the n squared minus n. And that's going to lead me to compare this to the sequence I'll call Bn. 1 over 4 to the nth power, or 1 over 4 to the nth power, where our sequence is the one given in our series, 1 over 4 to the n. So how does the sequence an compare to the sequence bn? In this case, if we want to come up with a inequality relationship, if possible, between these two expressions. Now the n values here, remember, are integers. They're positive integers, n equal 1, n equal 2, n equal 3. And so when n is 1, these two are actually equal to each other. But as soon as we reach 2, n equal 2, n equal 3, n equal 4, this plus n squared minus n portion is going to make the denominator of that term larger, and therefore make the number smaller. So we're going to have an inequality relationship like this for all n values. So our sequence an is always less than or equal to the terms of the sequence bn. And our sequence bn, we know its behavior. Bn is a geometric series, or it's a geometric sequence, so we know that the sum of 1 over 4 to the n, we know this converges, right, because this is a geometric series. With an r value of a fourth. So Bn gives rise to a convergent series. An is always less than or equal to Bn, and so by the direct comparison test, which is theorem 8.3.2, in particular, the first part of that theorem, our sequence also converges.